It's a cold, moonless night with a mist that hangs heavy in the air. As you turn to cross the road, fog swallows both the sound and headlights of the oncoming car. You see it too late and brace yourself for impact. Then, out of nowhere, an elderly stranger shoves you out of harm's way, is hit by the car, and ends up in a heap on the tarmac. Their life ends as yours is saved. Later, a police officer hands you an envelope found in the pocket of the deceased. It's addressed to you. You open the envelope and find a note with 2 words scribbled on it. It simply reads, "Study physics." Whoever wrote this note saved your life at the expense of theirs, so it only seems fair you follow their advice. Decades later, you become a much celebrated physics professor. Your specialist subject: Albert Einstein's theories of relativity. You've always had a hunch that time travel is possible. Then one day, finally, you crack it, and the world's very first time machine is buzzing before you. Only then does the penny drop. How had you never realized before? You now have the power to go anywhere and anywhen, but you know exactly what you have to do. You take the letter you've kept all these years out of its frame on the wall, place it back inside its original envelope, and put the envelope in your pocket. Stepping into your time machine, you set the controls to take you back to a cold, moonless, misty night, arriving just in time to push your younger self out of the path of the onrushing car. You die on the roadside. Simple enough it seems, but the real joy of time travel stories like this one comes once you begin to scratch beneath the surface, and some incredibly profound questions begin to emerge. First of all, who wrote the letter? The older version of you simply takes the letter they'd already been given as a teenager back in time. The letter is a seemingly creator-less entity stuck in a time loop. This is the bootstrap paradox. Secondly, do those time loops keep on repeating? You save your teenage self, so they grow up to travel back in time to save their teenage self, who grows up to travel back in time, and so on. You are stuck in a relentless cycle of living and dying, but the letter isn't. Does it just keep getting older and more worn and tattered? This is the restoration paradox. And whose idea was it to study physics anyway? The notion seems to appear out of nowhere, a thought with no origin. This is the ex nihilo paradox. If events like this can actually happen, then it also appears that you have no free will, no choices in life. You were always going to invent the time machine and had absolutely no option to do otherwise. It had to happen, had always happened. If you don't invent a time machine, then you can't save your teenage self, and you yourself would therefore die as a teenager. There is something in your future that's firmly fixed. This is called the predestination paradox. And finally, what if you change your mind? What if you decide not to trap yourself in the loop? Unfortunately for your older self, this is not an option. You can't get cold feet when you arrive and let the younger you get hit by the car. How could you be there to have second thoughts in the first place? This is the auto-infanticide paradox. It is seemingly impossible to kill a younger version of you, even through the act of not doing something. And so, not such a simple story. Welcome to the weird and wonderful world of time travel. But of course, traveling freely through time is impossible, you might say. You can't simply visit yesterday or rush headlong through millennia. And yet, this too is not quite so straightforward. Despite its myriad impracticalities, there are slivers of possibility lurking at the edge of physics, temporal loopholes lying just out of reach. In a distant corner of the universe, a gargantuan supermassive black hole is holding sway over an entire galaxy. Its intense gravity is pulling, stretching, and ripping up whole solar systems. Hot gas and dust whirl around it as its huge magnetic field spins up and spits out shrapnel into the void. Among the debris is a tiny subatomic bullet, a proton, which races across the cosmos at as close to the speed of light as it's practically possible to get. It has 100 quintillion times more energy than an ordinary particle of light, and after traveling over 1 billion light-years, it slams into Earth's atmosphere with 21 million times the energy of collisions inside the famed Large Hadron Collider at CERN. It's so energetic that to this day astronomers know it as the "oh my god" particle. An example of an ultra-high energy cosmic ray, it is a reminder that the Earth sits in a celestial shooting gallery. And when rays like this one strike our atmosphere, the impact is so violent that it bursts into an invisible fireworks display of subatomic particles. Pions, muons, and neutrinos erupt and cascade down to the ground. In fact, cosmic rays are so plentiful that they give you an annual dose of radiation equivalent to 3 chest X-rays. And for one Italian physicist, cosmic rays became an obsession. Is groundbreaking work on the muons created by cosmic rays producing some of the first evidence that time travel to the future is not only possible, but commonplace. His name was Bruno Rossi. Rossi is behind the wheel of an old bus, snaking along the highest road in the world where pine trees compete with snow-capped mountains to reach the sky. Eventually he arrives at the place he's driven over 1,000 miles from Chicago to reach Echo Lake. Nestled high up in the Mount Evans wilderness of Colorado, part of the world-famous Rocky Mountains, it sits almost 2,300 meters above sea level. Up in the Rockies, Rossi is measuring the muons created by cosmic rays. Muons are unstable particles, and so they quickly break down or decay. Physicists call the time it takes for half of a group of muons to make this change their half-life. It's just 1.56 millionths of a second. But Rossi's measurements reveal something curious. Far more muons are reaching the ground than there should be, even though the muons are traveling at more than 98% of the speed of light. Over 15 half-lives should still elapse by the time they make it down to Echo Lake, with each successive half-life removing 50% of the remaining muon population. Just 0.1% should reach Rossi. How come he is able to detect significantly more than that? The remarkable answer was that the muons were time-traveling into our future. Einstein's special theory of relativity says that you can think of anything moving through space-time as having a budget equal to the speed of light. The more of that budget you spend on moving fast through space, the less you spend on time. As the muons are traveling at close to the speed of light, considerably less time passes for them than for Rossi. From their perspective, fewer half-lives have elapsed, and so there simply hasn't been enough time for 99.9% of them to decay. This effect is called relativistic time dilation. When you factor it in, exactly the right number of muons reach the ground. Rossi had provided the first experimental evidence that time travel to the future is possible. But does this really count as time travel? First, imagine instead that you are the muon. But instead of traveling from the upper atmosphere to Echo Lake, you travel on a big loop around the universe at the same 98% of the speed of light, relative to those you leave behind, and return home 25 years older. Those of us left on Earth will have been spending less of our space-time budget on speed than you, and so it will cost us more in time. To us, you have spent your budget differently, forgoing time to travel through space. 25 years may have passed for you while you're gone, but 125 years have elapsed on Earth. You have skipped forward a whole century. Such a journey could mess with the normal generational order of family relationships, as is so poignantly explored in the short story Memories of My Mother by Ken Liu. So time travel to the future is more than possible. We just have to accelerate humans to close to light speed. That's far from straightforward, however. The faster you travel, the more energy you have. Einstein's famous equation E equals to mc squared tells us that energy and mass are interchangeable. So if you gain energy, you also gain mass. In other words, the faster you travel, the heavier you get to an outside observer. A person traveling at 99.99% of the speed of light would weigh almost 2 tons, or about the same as a rhino. Accelerating them to that speed would require as much energy as everyone on Earth currently uses in 3 months. Understandably, we are very far from pulling that off, but even today time dilation leads to some bizarre familial consequences. Take Mark and Scott Kelly, both former NASA astronauts who also happen to be twins. Mark was born 6 minutes before his brother. However, Scott has spent about 10 times longer in space, 520 days, to Mark's 54 days. During those extra days, Scott was whizzing through space-time faster than his brother, spending more of his budget on speed and less on time. In other words, more time has passed for Mark than for Scott. Mark may have started out life 6 minutes older than his twin, but he is now 6 minutes and 5 milliseconds older. Had Scott been traveling as fast as a muon instead, their age gap would have widened to nearly 6.5 years, despite initially being born on the same day. That weren't enough. There is another entirely separate form of experimentally verified time dilation. A second bona fide way to time travel into the future. Picture a clock. Except this clock works differently to any you've seen hanging on a wall. It is simply made of two horizontal mirrors. A beam of light bounces between the two mirrors, and every time the light hits a mirror, the clock ticks. Let's imagine you have two identical copies of this clock. You set them running before taking one of them deep inside a gravity well like the ones explored in the last section. Space-time is more curved inside a gravity well, and so the space-time between the clock's mirrors will also be curved. The beam of light will have no option but to follow this longer curved path. In other words, the clock will now tick less frequently than the clock you've left behind far from the gravity well. Bring them back together, and more time will have elapsed on the clock that did not encounter the gravity well. How can this be used to time travel into the future? Go and enter a deep gravity well, and then return to Earth. More time will have passed on Earth than for you. You can hop forward a century, just as you did by traveling at close to the speed of light earlier. However, to achieve a genuinely significant amount of time travel this way, you'll need a very deep gravity well indeed. One far bigger than the Sun's. A supermassive black hole should do the trick as long as you're careful not to get sucked in. Just such a scenario was used as a key plot point in the film Interstellar, suggested by the famous physicist Kip Thorne. But Earth also creates its own gravity well in space-time. When Rossi drove his bus up the winding road to Mount Evans, he was moving further out of this well. In other words, he moved from a region where space-time was more curved to a region where it was less curved. He aged at a fractionally faster rate up the mountain than he did down the mountain. The difference is so tiny that a human is never going to notice, but atomic clocks do. The best are such good timekeepers that they are accurate to within a 15 billionth of a second per year. If you sync up two atomic clocks on the same shelf of a laboratory and then place them on shelves of different heights, they will noticeably drift out of time. In 2022, physicists measured this gravitational time dilation using ultra-precise atomic clocks placed just a millimeter apart. You're likely to rely heavily on time dilation, probably without realizing it. GPS has become an indispensable part of modern life for many of us. Our phones and cars can tell where they are on Earth thanks to an armada of satellites swarming around the planet. The satellites send out time-stamped signals, and the quicker you receive one, the nearer you must be to that satellite. In order to achieve this, the satellites carry atomic clocks, which are subject to both forms of time dilation. They are moving through space-time faster than us and sit further outside Earth's gravity well. The time on the clocks has to be artificially altered in order to account for the fact that they are traveling through time at a different rate to us. These experiments leave physicists in little doubt that time travel to the future is possible. It is established scientific fact. But what about heading in the other direction? Is it possible to head upstream and visit the past? It's 2011. Barack Obama is president, Prince William and Kate Middleton are newlyweds, and NASA's iconic space shuttle lands for the last time. In September, physicists make a shock announcement, one that rocks the scientific establishment. They seem to have observed particles called neutrinos traveling faster than the speed of light. If true, it would shatter one of the holiest doctrines in physics and open the door to backwards time travel. The bold claim comes from the opera experiment buried deep under Italy's Gran Sasso mountain. designed to detect neutrinos fired 730 kilometers through the Earth from CERN near Geneva in Switzerland, making that journey at the speed of light would take a mere 2.4 milliseconds. Yet some of the neutrinos appear to be taking 60 nanoseconds less than that. In other words, they seem to have gotten there traveling faster than the speed of light. Einstein's special theory of relativity says that the speed of light is an impenetrable barrier. The faster you travel, the heavier you get. The heavier you get, the more energy it takes to increase your speed further. Eventually, there comes a point when it requires an infinite amount of energy to increase your speed. So you can't, and that cutoff point is the speed of light. While a massless particle of light can travel at light speed, anything with mass cannot reach light speed, let alone exceed it. And so inevitably, within a year, the neutrino mystery was solved. The experimental equipment was faulty. The neutrinos weren't superluminal after all. The initial finding caused such a stir because traveling faster than light would allow you to travel backwards in time. And the story of why starts with a young Dutchman by the name of Willem Jacob von Stockham. In 1937, von Stockham publishes a paper with the seemingly dull title of The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry. While mundane in name, it was revolutionary in nature, for it showed that Einstein's equations allow closed time-like curves in spacetime. Our world lines usually stretch from the past to the future, but a closed time-like curve is a world line that doubles back on itself, closing a loop as it intersects the line at a previous point. A pensioner following such world lines could revisit the moment of their birth, or even save their teenage self from a car accident. Von Stockham had demonstrated that, at least on paper, there is nothing in the general theory of relativity to forbid backwards time travel, except that at first glance it seems bending your future world line into a closed time-like curve requires you travel faster than light. To travel outside of what is known as your light cone. If your world line is the singular path that you actually take through the block universe, then your light cone represents all the paths that it would have been at least possible for you to take. Imagine that you are stationary in space, your world line moving forwards in a straight line through time only. What are your options for where you can go in the future? Well, assuming we stick with special relativity, you are confined by the fact that nothing can travel faster than the speed of light, which is approximately 300,000 kilometers per second. 1 second from now, you cannot be more than 300,000 kilometers away from where you are currently. Yet you could be up to 600,000 kilometers away in 2 seconds, and 900,000 kilometers away in 3. The further ahead in time you go, the bigger the region of spacetime that your future world line is allowed to be in becomes. That's why it's called a light cone. The edges of the cone represent the furthest a beam of light can be from where it starts at any given point in spacetime. Unless you can travel faster than a beam of light, you are trapped within the same light cone. And so, in order to loop your future world line around so that it intersects with itself, at an earlier point, you would have to leave your light cone. In other words, time travel to the past appears impossible, unless you can move faster than the speed of light. But there is another way to do it. If you constantly tilt your light cone so that your closed time-like curve to yesterday is always within it. And to do this, you would need to encounter spacetime with an incredibly high amount of curvature. In 1974, the American physicist Frank Tipler explored this very situation, specifically what would happen to a cylinder containing at least 10 times the mass of the Sun and rotating along its longest axis. He showed that following a precise spiraling trajectory around the cylinder would warp your local spacetime in such a way that your light cone would gradually tilt backwards. As your world line must be somewhere within the cone, you would then be ferried from the present to the past. Visiting a Tipler cylinder and then journeying back to Earth would see you arrive before you left in the first place. However, in order to tackle the fiendishly difficult mathematics, Tipler had to assume that the cylinder is infinitely long. He couldn't conclusively prove that a shorter one would do the trick. It would also have to rotate billions of times a minute to warp spacetime enough. hardly features of a practical time machine. Then, in the 1990s, Stephen Hawking added another layer of complexity. He argued that getting a tippler cylinder that isn't infinitely long to work as a time machine would also require huge amounts of negative energy. And it is here that quantum mechanics enters our story. One of the pillars of modern physics, alongside Einstein's general theory of relativity, it deals with the subatomic world. According to quantum physics, even empty space isn't truly empty. Pairs of so-called virtual particles are popping in and out of existence all the time. Energy is borrowed from the vacuum to create them, taking the local energy below zero in just the same way that your bank balance drops into negative territory when you go into your overdraft and borrow money from the bank. Just like the bank, however, the universe eventually wants its energy back. So negative energy is out there, but it's limited to tiny regions of space for fleetingly short amounts of time. As a result, closed time-like curves may exist in the subatomic realm, but creating a time loop big enough for a human to travel along to revisit the past seems an entirely different undertaking. There may be another way to achieve the same thing, though. A way to cheat the sacrosanct rule of the speed of light as the cosmic speed limit. A wormhole. In 1985, the celebrated astronomer, author, and TV presenter Carl Sagan published a novel called Contact. In it, an advanced alien civilization reaches out to humanity with the design of a device capable of sending a single person across the vast chasm of space to the star Vega. Taking into account that nothing can go faster than light, this 25 light-year journey should take an achingly long time. So instead, Sagan wants a way to get his heroine there far faster, but without invoking faster-than-light travel. Even though the book is finished, Sagan phones his friend Kip Thorne for advice. Sagan overnights the manuscript to Thorne, who reads it in the car the next day on his way to his daughter's graduation. A few quick calculations follow, and Thorne has the answer. What Sagan needs in his story is a wormhole. Imagine space-time as a sheet of paper with the Earth at one end and Vega at the other. Now, instead of traveling the length of the paper, you fold the paper in half. After all, we know that space-time can be curved and bent. Earth and Vega are now right on top of each other. Hop the gap between them, and you get there in no time at all. From the outside, it would look like you've got there by traveling faster than the speed of light. But at no point did you actually break through that sacred barrier. And so it follows that a wormhole can not only transport you to a different part of space, but it can also send you back in time. Let's say the wormhole to Vega is already set up. First, you need to attach the Earth mouth of the wormhole to a rocket and drag it round on a loop through the universe at close to the speed of light. As the wormhole has been spending more of its space-time budget on speed, less time will have elapsed from its perspective. So if you jump into the wormhole upon your return to Earth, you will emerge at the other end in the past. Crucially, though, you will also be in the Vega star system. So it is backwards time travel, but not heading back into Earth's history. There is still a way to pull that off too, though. Set the wormhole up in the right way, and the time difference between its mouths will be greater than the time it will take you to return to the Earth via the conventional route. You will arrive on Earth before you jumped into the wormhole in the first place. At least that's the theory. In practice, it gets a little more complicated. Thorne realized that the gravitational pull of anything traveling through the wormhole will act to pull it shut. You would need something to help prop it open. This could be negative energy again, but physicists have also explored the possibility of using everything from quantum entanglement to magnetic fields. In 1985, J. Richard Gott and William Hiscock solved Einstein's equations for cosmic strings. 6 years later, Gott realizes that they could also be used as a time machine. Just like spiraling around a tippler cylinder, take the right path along cosmic strings, and you could end up tilting your light cone backwards. Quantum entanglement has also been mooted as another option. Physicists know how to link two particles in such a way that changing one instantly changes the other, even if you separate them by huge distances. It's as if the information about the change you've made has traveled between the particles faster than the speed of light. But it has turned out to be impossible to actually transfer data superluminally using this method. So it seems that there are multiple ways you might be able to travel backwards in time without breaking the light speed barrier. But were it to be possible, what could you do about the paradoxes? Quantum theory might offer a solution there too. The handcuffs dig into your wrists and sweat streams down your face as you stare at the table in front of you. On that table rests a glass vial of lethal gas next to a hammer on the end of a robotic arm. A robotic arm connected to a machine that is constantly measuring subatomic particles. These particles can be in one of two states, A or B, and the chance of measuring each outcome it's effectively a convoluted coin toss. If the outcome of the measurement is A, nothing happens. But if it is B, the hammer falls, the vial is shattered and you die. The machine will make 100 measurements before the people watching from the other room will allow you to leave. Your odds of survival are around 1 in a million trillion. You can feel your heart pounding in your chest as the machine makes its first measurement. You relax slightly, only to tense up again ahead of the next measurement a few seconds later. And again. After the 10th A in a row, you begin to feel hopeful. Surely you can't survive this. After 99 consecutive as you're practically giddy. It all comes down to one final measurement. The machine clicks. Your captors are true to their word and unlock the handcuffs. You're free to go. Although you don't know it yet, your unlikely survival against seemingly impossible odds just provided possible proof of the many worlds interpretation of quantum theory, with potentially important consequences for resolving time travel paradoxes. This is a human version of the famous Schrödinger's cat thought experiment. The original imagined victim was a feline in a box with the same vial of poison and hammer. Quantum physics says that instead of being in state A or state B, the particle is initially in both state A and state B at the same time. Something physicists call a superposition of states. Except that means that the vial is also simultaneously unbroken and broken, and that the cat and you were both alive and dead until the point the next measurement is made. Is there something about actually making the measurement that forces the universe to finally choose one way or the other? Not according to the many worlds interpretation of quantum theory. Brainchild of physicist Hugh Everett Woolley. It says that every time there's an event in the quantum world that has more than one outcome, all outcomes happen. At that point, the universe fractures into two copies of itself. Outcome A happens in one, outcome B in the other. Reality is constantly branching off to fashion a tree of possibilities. The great river of time bifurcates into infinitely many separate streams. There are some in which you were never born and others where you are president of the earth. If true, making 100 measurements with the poison and hammer machine would have created 100 different branches of reality. You died in 99 of them and survived in one. As the sole surviving copy of yourself, you marvel at your own luck. The 99 copies of you in the other branches, though, aren't so fortuitous. Covering a sliding scale from those who died after one measurement to those who went through the whole process, only to die on the 100th. This is known as the quantum immortality experiment. There will always be a version of you that stubbornly refuses to die, no matter how many times the machine makes a measurement. It's a game of Russian roulette that you can never lose. While physicists do not know whether this interpretation of quantum physics is the right one, the many worlds theory could help us resolve many of the paradoxes often associated with time travel to the past. Take the most famous paradox of all, the grandfather paradox. You use your time machine to go back and murder your grandfather as a child. However, that means he never reaches adulthood, never meets your grandmother, and so your own mother is never born. If your own mother was never born, then you weren't either. How did you go back in time to murder your grandfather in the first place? Scientists, philosophers, and writers have come up with various ways to circumvent this issue. Stephen Hawking introduced what he called the chronology protection conjecture. It states that backwards time travel is simply impossible. The universe acts to rob you of any opportunity to go back in time. Cause and effect are sacrosanct and tightly policed. Igor Novikov mused on something similar. His eponymous self-consistency principle says that you can go back in time, but you can't change what's already happened. If you revisit an earlier page in the Book of the Block universe, you cannot rewrite what is already written there. Attempt to murder your younger self, and you will fail. Maybe the gun jams. Perhaps they sneeze and you miss. Try as you might, you could never succeed. But this, of course, raises other problems. Whether events in your future are predetermined, or whether free will exists. Nor would Novikov's self-consistency principle work in all cases, as Baruch Shoshani, Jared Wogan, and Jacob Hauser show in a series of papers published between 2020 and 2022. Imagine you have a working time machine. You also have a set of balls that are either black or white. Crucially, when two balls meet, the encounter changes their color. So a black ball becomes white, and a white ball becomes black. Let's say a black ball travels through the time machine where it whacks into its past self. This encounter changes both balls to white. The collision also knocks the ball that's already time-traveled onto a path that eventually sends it back through the time machine a second time. In this scenario, the exact same ball exits the exact same time machine at the exact same moment in the past, and yet it is seemingly two different colors when it does so. This peculiar paradox cannot be explained away using Novikov's self-consistency principle. But, according to Shoshani, Wogan, and Hauser, it can be explained using parallel time streams, the many worlds of quantum mechanics. They argue that time travel to the past is only possible if you emerge in a different stream from the one you left. So the black ball would start in time stream A, but would emerge from the time machine in time stream B. In this alternate time stream, it's the other ball that would end up going through the time machine after the collision instead, not the one that's been through once already. The ball that emerges from the time machine the first time is a different color from the one that emerges the second time. But that's now oak because it is no longer the same ball. This kind of extreme mental gymnastics takes some time to wrap your head around, but it does offer a potential solution to the grandfather paradox. If you enter a separate time stream when you go back in time, then you can kill the version of your grandfather there, safe in the knowledge that the version of your grandfather that's crucial to your logical existence remains alive and well in the time stream you left behind. Your free will is restored, giving you the choice to do whatever you want. It is possible to use many worlds to circumvent the bootstrap paradox too. In our tale of the time traveler saving their teenage self, the origin of the letter wasn't clear. No one seemed to write it, but perhaps we were missing characters from our story. The version of you in time stream A could write the letter, travel back in time to time stream B, and give it to their younger self. That teenager then chooses physics, grows up to invent the time machine, and travels back in time to time stream C to give their teenage self an apparently authorless letter. So we can explain the bootstrap paradox away, but we need the E versions of you existing in 3 separate time streams to do so. If that seems like using a sledgehammer to crack a nut, you're not alone. It could be a shining example of just how easily humans can tie themselves into intellectual knots. The number of splitting branches could be infinite. As the physicist Bryce DeWitt said, every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe is splitting our local world on Earth into myriad copies of itself. And John Wheeler, the very man who coined the phrase wormhole in the first place, fell out of love with the idea. I have reluctantly had to give up my support of that point of view in the end, because I'm afraid it carries too great a load of metaphysical baggage. And yet over the years the many worlds interpretation has gained traction with physicists, and now has a growing and loyal following. Of use, each a little different from the next, playing out every possible outcome of every possible event in constantly fracturing streams along the great river of time. And so, As we travel along our world lines at varying speeds within the great block universe around us, time travel to the future isn't just possible, but has already been done, and is being done every day. Traveling backwards is less clear, but it seems plausible, at least on paper, with a little helping hand from the counterintuitive world of quantum mechanics. For now, we'll just have to make do with memories of yesteryear, safe in the knowledge that the past is very much still out there.